Hello, my name is Cobarrubia. I'm a first-year PhD student in Computational Science Research Center. Today, I'll be talking about a project that I've been working with Karen Smith, Dr. Johnson, and Dr. Sankovitz on the classical emulation of quantum circuits with analog electronic circuits using multisim. In recent years, quantum circuits and quantum algorithms have been gaining scientific interest due to its potential ability to outperform any classical computer. However, the problem, quantum machines have yet to be fully realized for full-scale use. This requires classical emulators to simulate its quantum states. An alternative method to known software emulators is by implementing an emulated quantum circuit with hardware components. Specifically, we'll be using analog electronic circuits. Now, before we can begin deciding how an analog circuit emulates a quantum circuit, we need to know what is a quantum circuit. And essentially, a quantum circuit contains bits known as qubits, where it takes on the states of 0 and 1s. However, these states are determined by a quantum wave function. And if we and the tensor product and if we have an n qubit system, we can take the tensor product of all qubit states and form a general arbitrary wave function, as you see here in equation 1. We can also define a gate operation acting on a particular qubit on the wave function itself, as shown in equation 1b. The combination of these two, it can be represented as a graphical representation known as a quantum circuit, as shown in equation 2. And where here at the end, we measure the circuit to actually attain a measurement of the system. Now, how do we represent this in electronic devices? And the simplest case that we can do is by converting each basis states of our quantum wave function into a voltage wave signal. In particular, a complex exponential wave where we have some chosen frequency to represent a particular qubit in the quantum circuit, and an amplitude, a normalization amplitude to determine the quantum wave function's normalization. And since the basis states are represented by complex exponentials, essentially the real and imaginary parts are governed by cosine and sine waves, and these can be represented as wave function generators in analog circuits. And to multiply and create tensor products and inner products of two different wave functions or two different basis states, we use voltage multipliers to multiply these two different signals, and then operational amplifiers to add two quantum wave functions. And then at the end, the result of an inner product, we take the time average and we can find the actual emulated inner product, as well as coefficients and its matrix elements. Now that we have a general concept on how to build these, how to transform a quantum circuit into an emulated quantum circuit on an analog circuit device, we want to test case this using with the 3-qubit quantum Fourier transformation, as you see here in the top. And we do so by again initializing the state, and then measuring the state first by taking advantage of its classical nature of these wave functions, and then essentially do matrix vector multiplications for each gate operations, where the controlled and swap gates are determined by switching wires around to meet the specific needs. We then measure it at the end by essentially taking the time average of the state. And doing so, we did so for all 8 states for the 3-qubit example. And we find that the error, if we compare it to Qiskit simulation, that the error goes to 10 to the -3 order of magnitude, which suggests that our design captures the simple components of quantum wave function. In addition, we found that if we're only talking about voltage multipliers and some qualitative extension to all components, that each component will scale exponentially the number of qubits that need to be emulated. And however, even with this, in this case, we found that our Multisim design completely emulates the operations of the quantum circuit. Thank you.